Okay, good afternoon, everyone. Um, has everyone read the announcement that I posted today about the homework and the reading assignment? So what I'm going to do today is a little bit of active learning. So I'm going to go over the procedures to actually solve the homework. So if you have laptops out and you have your, you have your workspace out like a tablet, writing tablet or pen and paper, you can go along and calculate as we go along. I'm going to try and fit all problems in today's class. Okay. So let's bring up, let's see, where is the, oh, there it is. Okay, we stopped here, right? KVL. And then this, I assigned the previous one for practice. The first question in homework number 5 was 2.17. Now, these homework assignments belong in chapter 2. Chapter 2, we are only looking at Ohm's law, KVL, and KCL. You might have learned resistive circuit analysis. So we can solve these circuits using resistive circuit analysis. But the point is that you should learn or train yourself on how to solve these circuits simply by applying Ohm's law, KVL, and KCL, and nothing else. Okay. That is training yourself into the art of applying KVL and KCL quickly and efficiently. Because later on down the line, when we learn mesh current analysis and node voltage analysis, it will require application of KVL, KCL. Okay. So do not try to use or do not use resistive circuit analysis for these homework assignments. Use only KVL, KCL, and Ohm's law, nothing else. All right. So let's begin. Problem 2.17. Choosing only KVL, KCL, we need to find IA, IB, IX, which is the current going through here. I think we are given certain values. I don't have the exact problem in front of me, only have the circuit. So to determine IA and IB, I believe we are given VA. So this voltage is given. If you are looking at the problem at your end, the problem will be similar, but the values would be randomly assigned. So every student will have different values, okay, at your end. So let me see if I can bring up the question from, all right, let's see. Nielsen. 2.17 on 2.17. Where is it? Okay. No, that's not it. VX, V1. All right. I think I have IA, IB, power delivered, and power delivered by the source. Okay. All right. So we are given the value of VG. That's the power source. Power source. And then we are given the resistor values, and we are given, what else are we given? Value of IA, IB, and just VO. Okay, so we begin by applying KVL in the far right. So we have an equation right here. Now, obviously, these two are in parallel. So if you are parallel, you have the exact same voltage. Okay. As a reminder, in a parallel circuit, meaning when you have components in parallel, it does not mean that if one voltage, that the voltage remains constant. Okay. The voltage is constant across all elements in that parallel connection because the resulting voltage at both those nodes is a result of all elements acting at the same time. So in parallel, it does not mean that a parallel connection has 10 volts is going to remain at 10 volts. Okay. If the voltage changes to 8 volts, you have 8 volts across all of them. If it changes to 12 volts, you have 12 volts across all of them. So here we can write KVL in far right loop. And I can write minus VA plus VB is equal to 0. Therefore, VA is equal to VB. Again, I know that from parallel connections also. Then, because everything is an unknown, and I need to find IA and IB, I can find the voltage across RA by applying Ohm's law, and I can write VA is equal to IA times RA, and VB is going to be equal to IB times RB. V equals IR, right? V equals IR. So I have VA and I have VB. But VA is equal to VB. So I can substitute either one in the other equation, and I can find IA in terms of IB or find IB in terms of IA. Okay, because VA and VB are equal, right? VA and VB are equal. We can equate these two together. We can write IA times RA is equal to IB times RB. At this point, you can write IA is equal to IB times RB or RA, or we can write IB is equal to, I should have moved this to the left. Or I can describe IB as IA times RA or RB. Does that make sense to everyone? Right? You want to eliminate one of the variables, so we only need one equation to solve for it. So the steps, everything is an unknown. We have no idea what the voltage is. We have no idea what the current is. But we apply KVL at the far right, and we can obtain VA is equal to VB, parallel connection. Then we apply Ohm's law, write the equation V equals IR, so IA times RA and IB times RB. Equate both of them and substitute either one of them in the other equation, and we obtain an expression for IA or IB. And the purpose, of course, is that at the top, we have this total current IX, right? Total current IX. So if you apply KCL at the top, I can write IX is equal to IA plus IB. And now substitute either IA or IB. Okay, IA or IB. Wait to finish writing it down. Does this make sense so far? Once you have this, you will have IX times some constant times IA, or you will have IX is equal to some constant times IB. Okay. So you'll have IX, the total supply current coming from the power supply in terms of either IA or IB. You choose whichever one you want. Doesn't really matter. Okay. And once you have that, you can apply a KVL, or we can apply KVL in the left loop. We apply KVL in the left loop. Then I have my minus VG power source plus the voltage drop across RG. So that would be IX times RG plus VA is equal to 0. You see where this is going. right? Everybody take a look at that equation and reflect on it for a few seconds. So what do you think? We now have a KVL equation on the left. I'm sorry, over there, right? You got minus Vg plus Ix times Rg, Ohm's law, plus Va equals to 0. KVL holds true no matter which loop you use, right? Everything was an unknown. The only thing that we knew is that this is given, right? And from above, if Ix was expressed in terms of Ia, which is here, you can substitute it there. So now the entire equation is in terms of Ia. Va, of course, is Ia times Ra. There's only one unknown variable in that equation. Then you solve for Ia, and then you solve for Ib, and then you solve for all the other voltages. You can solve for the power. You can solve for anything once you have the answer for that one current. Okay. So basically, once you have Ia, you can solve for all other values. Okay. So while you're writing it down, I'm going to take it slow for this first one, and then we'll pick up the pace for the next few problems. Okay. So go over the steps. Okay. Ask questions if something doesn't make sense. Let me know if the steps make sense or not. And if students are online, feel free to speak up because I won't be monitoring the chat window. So if you have a question, we have a speaker in the classroom. I'll be able to hear. Okay, do the steps make sense? Right? The whole point or the purpose of going through all of this is we want to solve for unknown quantities in the circuit. The unknown quantities are voltage, current, power, energy, etc. In this case, it seems as if there's no good way to start without solving for the resistors. But by an application of Ohm's law and KVL and KCL, we can apply them in any sequence we want. The point is we should solve for at least one variable. As an engineer, when you begin circuit analysis for an unknown circuit, which is what you'll be doing as an EE for a while, it's completely new circuit, it's completely unknown. So you need to pick a starting point. It may turn out that the starting point is not correct, so it doesn't really matter. You go back and pick another starting point. In this case, of course, the solution is provided. We already know it. If it's a new circuit that I do, then I go through multiple steps, and then I know which step to start with. So in this case, we are just starting with KVL at the far right loop. The goal is to eliminate as many variables as possible and get one single equation which has only one variable, which is right here. So that should be the approach for all of the problems. If you have one unknown variable, you need at least one equation to solve them. If you have two unknown variables, you need two equations. Three unknown variables, three equations, and so on and so forth. So the goal here is to get at least one equation to solve for one variable. Okay. And once you have the answer for that, you can solve for everything else. Okay. All right. So I'm going to move on because it's already 50. Yes, go ahead. I think the voltage of the power supply was given and the resistor values were given. So the question being asked is what is given in the problem? The only thing that were given was the power supply VG and the resistor values, the three resistor values. So again, at first glance, at first observation, it seems that we cannot solve this without reducing the circuit, but that's not the case. So the point is not solving the circuit. The point is learning how you can apply these different methods to larger circuits. Okay. All right. So let's get to 2.18. So in 2.18, you have a voltage source and voltage source. Let me bring up the question here. So the question is, we have currents I1 and I2. So there should be I1 right there. We have Vx over here. You have Ix over here. And again, you have the supply voltage, Vg. Supply voltage is given. Resistor values are given. And we just need to find I1, Ix, current going down here, and the voltage across at the far right, which is given as V1. So we can label all of them. I don't particularly agree with what they have done actually. So they have Ix here with this resistor at the top, and they have Vx here with the 5 kilo ohm. Typically, if I have a subscript, meaning I have IR1 or IR2, then a corresponding voltage would be VR1 and VR2. So I would prefer to have Vx and Ix for the same resistor, not for different ones. Anyway, so that's I1. I'm going to call this I2. I think the online system would have like a different nomenclature, but the approach remains the same. Okay. Stuff voltage value. I believe Vx voltage value is given in the problem. Okay. Vx is given, so Vg is given. Vx is also given. Okay. Vx and Vg are both given. Let me just confirm. I believe they are. Let's see. So the next one is I1, I2. So, oh, maybe not. Hold on. Where is I1, I2? Vx is 3.5. 19 and 21. Okay. So I believe, yeah, Vg and Vx are given, and we are required to find the other values. So we can find, since Vx is given and the 5 kilo ohm resistor is given, we can simply apply Ohm's law and determine I2. Okay, yes. Okay, Vg is not given, Ix and Vx are given. Okay, all right, so Vg is not given, Ix and Vx are given. Thank you. All right, so we can apply Ohm's law and we can find, let's see, so if that's the case, I'm going to call this, let's call this VA, that's Vx, let's call this VB, as V1 and Vx. It makes a mess of notations. Since Ix is given, we can find VA. VA is simply Ix times, yeah, I don't know what that resistor is. Let's say 2 kilo ohm. That's from Ohm's law. I can find I2 from Vx or 5K. And once I have that, I can apply KCL at the top. And KCL at the top gives me Ix is equal to I2 plus I1. Since I already have Ix, since I already have I2, I can find I1. I1 is Ix minus I2. Once I have I1, I can find the voltages across the two resistors on the far right, and I can find VB and V1. Okay. And once you have Vx and Va, KVL either in the outer loop, meaning the big outer loop, or in the left loop to find VG. And once you have the voltage and the current, easy to find the power equation. Do the steps make sense? $32. I think I have how many problems? 1, 2, 3, 4, 5, 6 more problems to go. Okay. All right. So I'm going to move on. 19. Problem number 19. All right. So current source 4 amps is given. Resistor values are given. R1, R2, and R3. And then what else is given? Can you check online and let me know? And then the current source is given. Okay. All right. So the question being asked is find I1 and I2. Right. 1, 3, 9. Current source 9. Oh, and also find VO. So VO, I1, I2. Calculate all three of those. Okay. And then, of course, the power for all of them. So we can start with, let's see, current sources given. So we cannot start with Ohm's law because I1 and I2 are not available to us. We cannot start with KVL because VO is not available. So the only logical option is to write a KCL at the top. Okay. So we begin with KCL. KCL at the top. And I can write 4 amp source is split into I1 plus I2. Okay. So that's the only logical place to start. I1 plus I2 is equal to 4. At least I have 4 in here. You might have a different value at your end. Okay. Straightforward, current source, current splitting into 2 different paths. So once you have this equation, you can describe I1 in terms of I2 or I2 in terms of I1. You can write I1 is equal to 4 minus I2, or I2 is equal to 4 minus I1. Again, the goal is that there are 2 unknowns, I1 and I2. So if we have an equation that contains both I1 and I2, we replace it with the other equation from here. And then the only unknown left in there would be either I1 or I2. And we'd be able to solve for that. So now since we have an equation for I1 and I2, we can write a KVL. We can apply KVL for the far right. Obviously, you cannot write a KVL in the left loop. There's a current source and there's a voltage that's unknown. So KVL in the right loop. And I can write what we have. Let's call it VR1. Since the current is coming down, plus is at the top, minus is at the bottom. Plus on the left, minus is here, plus at the top, minus at the bottom. So I can write minus VR1 plus VR2 plus VR3 is equal to 0. Okay. Again, KVL you can apply with your preferred method. Now, VR1 is going to be minus I1 times R1 plus I2 times R2 plus I2 times R3 equal to 0. So simply applied Ohm's law and expressed each voltage drop in terms of the current and the resistance. Now you can substitute. You have I1 and I2, right? Substitute either equation in that KVL expression, and you'll be left with only one variable, either I1 or I2. Make sense? So once you substitute, only one variable will be left, either I1 or I2. Right? And once you have only one variable left, you can solve for that variable, solve for I1 and then I2. Once you have I1 and I2, you can solve for all the voltages. You can solve for the voltages. Once you have solved for all the voltages, you apply KVL to solve for VO. Okay, so the steps are, write KCL at the top. You obtain a relationship for I1 and I2. You already know the sum total of both currents is 4 amps, the current source. So express either I1 in terms of I2 or express I2 in terms of I1. Write the KVL for the 3 resistor voltages. Once you write the KVL, apply Ohm's law, substitute I1 and I2 in that equation. And then from these two, pick either one and substitute it in here. That gives you one equation with only one variable. Solve for that variable, whether it's I1 or I2, and you have your answer. Then you solve for the other one. Once you have both currents, apply Ohm's law to all 3 resistors, find the voltage. Once you have all 3 voltages, apply KVL and find the current source voltage. Make sense? Okay. All right. And then I'm not getting into the power. So every question asks for the power, but the power is, again, if you have a resistance, power is V times R. Electrical power is the product of voltage and current, always. You're going to use this equation throughout, even for AC analysis in next 211 and 212. Okay. In terms of resistor, it's I squared times R and V squared over R. So you should be able to find power for all components. All right, 3:40, 20 minutes left. I'll pick up even more. So now we have question with 2 sources, voltage source and a current source. Okay, that's 21. And then let's see. It's 21 and that's 25. So let me do one more thing. Because homework 6 is about dependent sources. Okay, since I've covered like 3 problems here and I have only 20 minutes left, I might, let's get to homework 6, so dependent sources. Okay, I'm going to skip over these for now. And then if you have time, I'll come back to them. But I'll get started with this one. So 32, 33, and 36, they all have dependent sources. Okay, so how do we solve circuits with dependent sources using only Ohm's law, KVL, and KCL? So let's start with, actually, let me do this one. This one has 3 sources, the most Seems the most complicated one. So let's do that one first. And then if time permits, we'll go to the other ones. All right, so question is, we have, let's see, what are the given values? We are given, okay, we are given the value of VG, and please let me know if I'm incorrect. I think VG is given, and then so is the value of the dependent sources, right? 20 IA, no, 20 I sigma and 8 I delta. Okay, I sigma and delta. All right, so this is I sigma. It's a Greek letter, and I sigma is right here. And then you have I delta right here. That's I delta right here. So these voltage sources and current sources are dependent on these two these two currents going through the 18 ohm and the 40 ohm resistor. Okay. And so the value of the voltage source VG is given, and the far right voltage source is also given. So how can we apply KVL, KCL, and Ohm's law to solve for these? All right. So let's look at that. 36. Mine, the question is a little different. It's weird. Okay. All right. So the first thing we're going to do is we can write a KVL expression where we have all the voltages, or we can write KCL, but KCL doesn't help because the sources, all three of these sources are dependent on these currents, I delta and I sigma. Okay, so the KCL is not going to help in this case. Perhaps for a different circuit it might, but for this one it doesn't. Since we are given the power supply voltage on the far left and we have the power supply voltage on the far right, KVL makes the most sense. But if we write a KVL around the outer loop, if we apply a KVL around the outer loop, we don't know the voltage across this current source on the far right. So even that one kind of doesn't make sense. If we do apply it, let's see. It kind of doesn't. All right. So what we can do is we can apply, actually, you know what? Let me name these loops. So I'll call this L1, L2, L3. Okay. I could apply KVL in L1 because they're all voltages. I could also apply KVL in L1 plus L2. Again, all voltages, right? See, apply KVL to L1, and I obtain minus VG minus 20 times I sigma plus 18 times I delta. Right? I have 18 ohms here. You might have some other resistor. And that would sum up to 0. So I have one equation with two unknowns. Right? Two unknowns are I sigma and I delta. So you have sigma and I delta. So if you have two unknowns, we can either try and reduce them to one unknown variable, or we write another equation that has two unknowns and we can solve those simultaneous equations. Okay. So one of the ways we can do that, again, is what the technique that we used in the previous one. We find a relationship between the two currents. So if we solve for this, I can write, well, VG is given at my end in the problem. I think it's 20 volts or 50 volts. And then I can analyze and write this as some constant times I sigma is equal to some constant times I delta. And from here, I can express either I sigma as some constant times I delta, or I delta is equal to some constant. Actually, let me not use this. It looks too much like a minus sign. So some constant times I sigma. Again, it helps that there are only two unknown variables in there, right? So we only have to reduce it once. Okay, it's a dependent source, but the approach is exactly the same as the first one that we did, 2.17. Two unknown currents. We are expressing each one of these currents in terms of the other one. And now we can pick and choose either one and plug it into here. We plug it into that equation. We can solve for VG. Okay. So once we have the values for the currents, we can solve for the other current value. Once we have those currents, we can find the value of the voltages, right? So you solve. So from here, let me go up here, solve for both currents. And once you solve for both currents are flowing through 18 ohms and 40 ohm. So from here, you apply Ohm's law and solve for the voltages. So I delta times 18 will give you some voltage. And then I sigma times 40 will give you some voltage. Okay. And once you have those voltages, this is, by the way, this is VO. Once you have those voltages, apply KVL to, oh, VG is given, sorry, VG is given, so we don't need to find VG. I1 and I2 are the only ones that we need to find. Okay, so once we find I1 and I2, find the power dissipated of the voltage across both resistors, power dissipated in all the resistors, power associated with all the other sources, equate them, and you have your answers. Okay. So at first glance, it seems complicated because there are like three dependent sources in there. But again, the dependency is on two of those currents. So it's very similar to the first problem that we did today, which is 2.17. You have two unknown currents, write a KCL or KVL expression, whichever one works for the circuit, and then you express either one of the currents in terms of the other two. And you can just plug it back into the first equation and solve for that unknown variable. Once you get one answer, you can find the second one. All right, let's take a pause. Let me know if you have any questions. This is a quick, small pause. Do the steps make sense? Okay. All right, so then let's go back. So that's the end, but let's go back to 2.33. So in 2.33, we have three independent sources and one dependent source. Okay, one dependent source. So what we excuse me. At my end, what does it show? There's the question. Okay, so I1 is given, right? For this one? Is I1 given in the problem? So V1 and V2 are given. Value for I1 is not. Oh, I1 we can calculate easily. Okay. So we have two voltage sources connected on either side of the 54 kilo ohm resistor. What does that mean? Well, if V1 has a particular value, positive, I can find voltage for the 54 kilo ohm resistor. Right? Don't even have to apply KVL or anything. It's just simple voltage difference between the two endpoints. 5 minus 1. If you're measuring from left to right, it becomes minus 4 volts because the current is shown as going from left to right. Right? So the lower end of the resistor, right there, you're measuring from left to right, difference is just magnitude of the difference is 4 volts. So we can find the current flowing through that resistor. Okay. So voltage is the difference between V1 and 1 volt. Then apply Ohm's law. To find I1. Once you have I1, you can apply, let's see, what else is given? This voltage is not given, right? This V is not given. So we need to find that. But we are given the dependency. So it's 30 times I1. So now we know the current that is flowing in this loop. So from I1, calculate 30 times I1. Once you calculate 30 times I1, you can calculate the voltage across the 1.8 kilo ohm resistor. And once you have that voltage, you can apply KCL at the top and can find the current flowing through the 6 kilo ohm resistor as I1 plus 30 times I1. And from there, you apply Ohm's law and you find 6VK is I6K times 6K. Okay. The steps make sense. Do you have any questions? Yes. Okay. So the question being asked is how do we find the voltage across the 54K ohm? If you want to take it step by step, we can apply KVL and find it. But in this case, we know that voltage is simply the difference in electric potential between any 2 points. So if you take the 54K resistor, one end is 5 volts, the other end is 1 volt. Both ends, the positive terminal is connected. All it means is when you have 5 volts and 1 volt, if I draw a one-dimensional chart, if I say this is 0 volts, this is 1 volt, 2 volts, 3 volts, 4 volts, and 5 volts. 5 volts simply means that point, this point in the top left, is 5 volts above 0 level. And this point is 1 volt above 0 level. So the difference between the two is 4 volts. Now the magnitude depends on how we are measuring. If I measure with this plus and this minus, the voltage across that resistor would be plus 4 volts. If I measure with my reference here and here, that would be minus 4 volts. Current is shown to us as flowing in this direction. So we would take this as positive and this as negative. And so I would say this would be 4 volts in this direction. Okay. So that current matches the polarity of the voltage. Okay. And so if that's the case, we have 4 volts, and then we simply apply Ohm's law. We find the current, I1, and then find everything else based on that. So there's about 3 minutes left. We'll like rush through stuff, but I think we have covered enough so that students would be able to solve for themselves. If you get stuck, send me an email, reach out to me. I will be in my office tomorrow, so if you want to stop by, just let me know. I want to do, since we are talking about two-dimensional voltages, let me just do some fundamental concepts of voltages, okay? This is going to be quick. Let's say we have, this is 0 volts, okay? And I'm going to call this point A. Point A is at 0 volts. And this is just a one-dimensional chart in the y direction, okay? And then point A, I have point B somewhere up there. So it's 1, 2, 3, 4, 5. So this is at 5 volts. Point B is at 5 volts. Point C is at 4 volts. Point D is at 2 volts. Point E is 1 volt. So I'm counting as a distance from A, okay? And point F is at 2 volts, okay? If A is my reference, 0 volts, what is the distance at, so D is at 2 volts or 2 units above A. So what is the voltage at D? 2 volts, plus 2 volts, right? If my reference point or measurement is at E, what is the value of VD? You can see the distance. Is A is reference, then VA is 0 volts. Therefore, VD is equal to 2 volts. If E is reference, what is VD? How much do you count? 1 and 2, 3 volts. It's 3 volts. Now, if VD is my reference, sorry, not VD, if D is the reference, then VD is equal to 0, okay? VA is below VD, so VA is minus 2 volts, VE is minus 3 volts, and VF is minus 5 volts. The important point is your reference point matters. The reference point is the point where you connect the negative end of your multimeter. If your reference point is the floor of this room, my height is barely 5'6", so 5 foot 5.5. So 5'6", my height measured from the floor is still 5'6". If I jump onto this table, it's, I don't know, about 4 feet, let's say. So then my height is not 9.5 feet. It is still 5.5 feet. The distance remains the same, but the point of reference changes. So you can say that the top end, I mean, the place where we are measuring with your reference point has increased, but the distance between the points do not change. So anytime in a circuit when you are trying to measure different points on voltages, you keep this in mind, okay? So we have rushed through this, but take your own time, go through this fundamental concept, and then if you have questions, please reach out, okay? So we're going to end class here today, and I will see you all on Friday.